Yeah, so this is my third talk now here, and I've already explained a lot about radio telescopes before, so I don't know if others saw my talk, so I'm not going to explain too much about radio telescopes, more about Python. So, yeah, my name is Gijs Molenaar, I'm a scientific software engineer, and half of the time I actually work in Cape Town. So I have this really nice deal that in summer I live in Amsterdam, and in summer I live in Cape Town. So I have endless summer, which is great. And Cape Town is just absolutely amazing. I absolutely love this town. So who has the people been there? Who has been there? Yeah, so do you agree? It's food is great, weather is amazing. There are some problems, you know, but it's just an amazing country. So I work on radio telescopes. I work there on Meerkat, which is a predecessor of SKA. And SKA will be one of the biggest scientific devices ever made by mankind. And in the Netherlands, I work on LOFAR, which is near Dwingelo, which is a smaller radio telescope. And both are quite unique in design and how they process their data. And yes. So I'm going to take you on a tour. So we're here now, and this is Europe, if you didn't know. And then we go down to Africa. I'm going to take you to Africa. And which is very far away. It's 10 megameters, and so there's Cape Town, and then we zoom into the desert, and then into the nothing, the Big Karoo it's called. It's about 10 hours driving from Cape Town, and then we see this thing. So this is, I think, about 2 kilometers in diameter, and this is what they're building now. So this is called Meerkat, and when you're in a plane, it looks like this. So they have a small plane going there to change the crew. So there's a crew working in shifts to operate this thing, and some of the dishes are already operational. So yeah, this is a radio telescope. It will be 64 dishes. I think about 4 of them are operational now, and then during the upcoming year, all of them will get operational. So you can see that it's not being used now yet, because one of the dishes is actually pointing to us. And the equipment is so sensitive that if a plane would pass by on this distance, it would emit so much electromagnetic radiation that it would fry all the equipment. So it's so usually when the plane comes, which happens once a week, all the dishes are pointing the other way, so you don't fry the equipment. So I went there with this small little plane, which was amazing. They had a spare spot, and once a week you can go there, and at the end of the day go back. And it really had this like James Bond feeling where you fly to a hidden secret experiment, and they have this huge data center under the ground with hundreds of servers, and they do a lot of processing with microcontrollers also. They're designing their own hardware called Scarabée, and there's a droid spa where they put it in liquid oil to cool it and bury it under the ground. So a lot of stuff happening, but I'm not involved in that. I'm later in the data pipeline. But so yeah, this is a close-up of one of these dishes. This is one Meerkat dish. There's 64 of these. They're about 20 meters high. That's me next to it. So they're just huge, and they're awesome. They are used for various things. One of them is for making images, astronomical images, and that's done with a process called interferometry. So I'm not going to explain it now, but the result is images like this. So this is Cygnus A. This is one of the brightest radio sources in the sky, the dot in the middle actually, but when you look at it more closely, you see these jets, which are caused by, I don't know, it's like, I'm not an astronomer, but it's a binary system, and one of these stars eats the other star, and then the speed of the descent to the other planet is too fast, and you get these jets that are very fast and very far away. So I think this is like almost the size of the Milky Way, but I'm not sure. I'm not an astronomer. So this is not optical. Like a classical telescope, it looks in the optical spectrum, but there's much more electromagnetic radiation. There's X-ray, gamma ray, there's microwave, infrared, and radio. So we really look into radio, which is very low frequencies. You cannot see that with your eye, but you can see it with antennas. And with multiple antennas, you can create images from that. So the data rates coming from these telescopes are enormous, gigantic. We really have big data. So the raw data rates are about 4 terabits per second. So there's 64 digits generating 4 terabits. So this is quickly reduced. So we have a data reduction pipeline. It's quickly reduced into more manageable shape. So, as I said before, we have all this embedded programming stuff happening, which does the first step called correlation, and then another cleaning, flagging. If there's bad data, dump it, and then it's being transported to Cape Town, where it's stored for a little while, and then astronomers can use this data to generate their images or do other funky stuff with it. So, but then still, the data rates are about 3.2 gigabits per second. So I'm more specialized in the imaging pipeline, or I work with the scientists who do this imaging. So I see myself as more as a sort of plumber that sort of knows what the astronomers do. And so I work with the astronomers that do the imaging. And so a typical use case for an astronomer is to take this, like a specific time set of these recordings, of this data, and then transfer it to a big supercomputer or a cluster, and then apply their scientific software on it to make images and to clean the images. So the telescope has its intrinsic problem. There's all kind of artifacts introduced by the hardware, and there's noise and stuff, and you can try to clean that out. And that's actually an active research field. So actually, we're not using this one anymore. It's just a nice picture. So this was the old calibrator of LOFAR. Just to be honest here. So that's. So yeah, I work with the people who do imaging and calibration, and so making the actual image and then cleaning it up, making it look more nice. So and it's a bit similar to MRI imaging. So I'm already talking too much about astronomy. So I work with the scientists, and they create software, and they use software, but often or sometimes the software is not that good. It's fragile. They don't really know how to use the build tools. It's C, C++, a lot of Python, a bit of Fortran. And other astronomers that need to use this software, they struggle to get this running on their system or on their cluster. So when I started working there, the first thing I started doing was creating Ubuntu packages of all these pieces of software, so it's much easier to install them. So we have this Launchpad PPA. I get the idea. Everybody is nowadays in web development, and so this is like old school daddy technology. But it's actually really nice that Canonical, the maintainer of Ubuntu, has this build farm where you can just upload your packages, and it builds it for various architectures, and then other people can install these packages. There's different solutions. We're always looking into new, better ways to do this, but we use this Launchpad PPA now. And a lot of astronomers are really happy with it. So the next step, of course, because that's what everybody is doing now, is containerize it. And I think everybody know what's Docker here. I think, who doesn't know what is Docker? Good, yeah. So actually 3 years ago I was here, the keynote speaker said like, oh, you need to look at Docker. So then I started looking at Docker, so that was great. It was great inspiration. So yeah, Docker is a self-contained, lightweight virtual machine without virtualization. It's just a little file system where you can run your application in, and then it thinks that it's inside this virtual environment. And somebody once told me it's sort of like centralized agony. So there's only one person that has to suffer creating this container, and then the rest of the world can enjoy it. So once you have these containers, it's really nice to install or transport or deploy your applications. So we have these micro or mini containers, right? So we make these small containers with one tool. And what else can you do with it? So I tried to be a scientist and try to come up with new inventions. So we were sitting around the table like, what can we do with this? So when you look at our pipelines, also the imaging pipeline itself is a pipeline, various tools. And you have this one process taking data in, generating data, and then there's another consumer taking data in and generating more data, and then there's like similar processes taking data in, and then that data is combined, fan in, fan out. So we see this kind of patterns a lot in our pipelines, and well, until now, a lot of these things are manually created with bash scripts and hacked together with awful Python code. So I wanted to improve this a bit. So why not use Docker for this? So I have all these little modules, Docker, and then combine them together, and like similar like Docker Compose, how you can take all these services and connect them together. So the problem is we cannot really use tools like Docker Compose because those are service-oriented, right? So you have a database, you have a Redis cache, you have a web server, and that runs an application, and once a request comes in, so they are connected on a network level, not really on a data flow level. So I was looking around and I couldn't really find something like that. Maybe I'm blind, but I really couldn't find something. And so if you want to do this, there's a couple of problems that you have. So Docker is really nice for containing the software, but it's not obvious how the data flow should go. So it's like, how does the output look like, and where does it go? Where does the input go like, and how do you configure the software? Well, you can like mount in a config file, but then every container has a different config file. So to solve these problems, these three problems basically, I came up with the Kliko compute container format. So Kliko is basically assuming that your problem looks like, hey, you want to take a picture? Yeah. So so your problem should look like this, right? You have a Docker container, and it has software, and it has some parameters, like some integers, or some strings, or some dictionary, or whatever. And it has some data input, it does something with this data, and then it generates output. That's Kliko, that's it. So how do we do this? So then I wrote a Kliko specification, which is quite a formal list of things. Okay, Kliko containers should comply to these things. So it should read the input from /input. So if you're in the container, you should read your input from /input. And then if you do something, write your output to /output. There should be a Kliko YAML file, which looks a bit like on the left, which has some parameter or some descriptive fields, and then it has a set of sections containing parameters, or a description of parameters. Not the parameter itself, it defines which parameters this Kliko container accepts. So if you are making a Kliko container, you can write this Kliko file and saying, okay, I'm making this calibrator, and it accepts 5 integers representing this and this and this, and you can describe them, give a little bit of help, and blah, blah, blah. So, and then also there is a Kliko entry point script, which is just a whatever. Could be Go, could be Python. And so it's preferably Python, because I also made the Kliko library, which you can include inside your Kliko script. And then you can just do parse, and then it would parse everything, check if everything is valid, and it would return a dictionary giving the parameters which are put into the Kliko container by the Kliko runner, which I'll explain later what it is. Yeah, so now we go to the Kliko runner. So, so you have 2 components. You have the Kliko container, and then you have something that runs the Kliko container. It's a Kliko runner, which you can make yourself. I made 2 example implementations. I'll show you them later. But they run containers, and they read in the Kliko YAML file and say, okay, we have these sections, we have these fields, what should be in there? And depending on the Kliko runner, it can present the user with a menu or a web interface saying, okay, we have these fields, and you can fill something in. It can fill it in, or it's maybe stored in a database or whatever. Like it just has this data. It generates a parameters file from that, and it will mount it inside the Kliko container. And then it will start the container, and it maps the right input and output to the right location. So I made a command line one, Kliko run. I have this Kliko test container, which I listed here before. It just has some like choice fields, which you can list which choices there are, and some characters, which I should rename to string. and integer and float, stuff like that. And then if you run this container, then with the -- help flag for the command line, it will show you all the parameters that are available. So this is basically just some helper functions that I implemented in Kliko that makes it possible to take a parameters file and then render this, what is it, Python string parsing library. So it will generate the whole command line parsing tree for you with all the options and check if it's valid and stuff. So you cannot put wrong stuff in there. There's also a web interface, which is just a simple Django project, which just does exactly the same. Basically, in the Django admin panel, you can just add some Kliko containers, and then other people who log into the website, they can run jobs, pre-configured jobs, and they can. So this is perfect for radio astronomers that don't know anything about computers, right? So they get this menu with all with descriptions and integers and floats, and pull-down menus, and they press simulate, and then it does some computing, and then the web interface will visualize the results. So depending on the time, I can give a quick demo later. So what else is Kliko? I made a typo there, I see. So it's a set of runners that I just showed you. It's a set of validators to check if everything is valid. Is the Kliko.yml file in the right syntax? It will give you hinting, or if there is a typo somewhere. Also, it checks if the parameters file that is mounted into the Kliko container by the Kliko runner is actually valid from this Kliko YML file. So is everything matching? Are all the fields filled in? So, but Kliko as a library is usable inside and outside the containers, so for running the containers, but also parsing all the stuff inside the container. So what kind of other funky things you can do with this? So yeah, so so it's not a requirement for Kliko, but you can make a functional container. So this is an idea, a concept borrowed from functional programming, and a functional function means that you have a function without side effects, which means that whenever you call it, like now or next week or on the other computer, and you give it a specific set of parameters, it will always return the same result. So there's no caching, there's no there's no caching, there's no time-dependent calculation happening. So for example, like a database query is a typical example, which is probably not functional, because depending on what's there in the database, it would return different results. So if you have a functional container, you can do all kinds of interesting things, like, for example, caching results. So what you often see is that you have a job which takes maybe 10 hours to run, and then step 9 fails, and then worst case, you need to rerun the whole pipeline. So it's awesome if you could just reuse all those results. So this is not implemented yet, right? So just a description of what is possible with this. So Kliko itself is just a micro library, and then I want to make a new library that would implement this. So also you can do implicit parallelization. So if you have jobs that don't depend on each other, you can just run them simultaneously. So you can do inference on which job you can run, and you can just have this whole mesh of Docker containers running in your cloud infrastructure. So another recently nice new thing that was introduced in Docker was Docker volume plugins, and made all kind of interesting Docker volume plugins for Amazon S3 and OpenStack. I don't remember how their storage is called, and CAPH, which is this supercomputing data storage format, and so they all support this kind of stuff. And the cool thing is that you have this big storage thing with a lot of drives, and you can just say, okay, I want to have a volume of 1 gigabyte, and I want to attach it to this input or output, and so that's completely transparent, right? So, but Kliko doesn't need to know about that. That's the beauty. So if you want to have a new storage engine, you can just write a new Docker volume plugin, and this thing works. So it's, of course, not all sunshine and amazing. The problem is when you have streaming data. So you have processes that stream data. So that's where we want to go. So I didn't mention that, but a lot of these tools are a bit stupid, actually, that what they do is that everything is file system based. So you have this huge data set of 10 gigabytes astronomical observations, which is stored in this radio astronomical format. It reads it in chunks into memory and then writes it down again. So you constantly copy data around, or you modify the data in place, which makes it not functional anymore. So there's all kind of problems there. So, but we recognize that, and actually, we know that. So, so Kliko is actually designed for that, right? So that you read in your data and write it out. So if you don't have huge data sets, it's not a problem. But if you have, it is. We have huge data sets, but that's how our tools work. Well, so we're going to work on this streaming way, which changes the problem into more of a Docker Compose thing, where you have services with streaming data. So also Kliko is not limited to radio astronomy, right? It's just a generic tool. So there's no radio astronomy anywhere in the documentation or whatever. Or maybe it is, I don't know. So also this is not limited to Docker. I should work with Rocket. I forgot how you spell Rocket, but I think it's like this. And maybe LXC, but I didn't try it yet. But in theory, it should just work. And maybe it's even better to use LXC because, well, everybody's using Docker, but there's some really fundamental problems still with it, which are hard to solve, which maybe will be solved in the next year or two, but there are problems. And one of the problems is that if you give somebody access to the Docker engine, and effectively this person can escalate to root easily. And there's all kind of security measures you can do, but basically, yeah, if you can run a Docker container, you can take over the system, which is not really a good thing. They're working on it. There's all kind of like technical details. You can talk about it later if you want. So also GPU acceleration is hard. If you use NVIDIA, I don't know how it is with AMD, but we use NVIDIA, a lot of NVIDIA. And the problem is that the library version needs to match the kernel version on an NVIDIA level. So the whole abstraction of hardware and software independence breaks down, or host and guest independence break down. They need to match. So NVIDIA made a solution for that, where you have a separate NVIDIA binary runner wrapper, and which sucks. So also the whole cached file system layer thing. In the beginning, you're using Docker, it's like, oh, this is awesome, all the commands are cached. And then you discover that it's actually really annoying when you use like Debian package management, and when you update your cache and stuff gets outdated, and it really gets into the way. And I didn't really find a good way to just disable this. And or just you get these weird hacks. So I really don't like it. I really started to hate it. And another problem is that you can't really combine containers. So you have this nice feature where you can inherit containers, and you can make more specialized containers. So you have your base image, and say, okay, I have this container with this software installed, and then this software installed. But sometimes it's really, really useful to have containers that have multiple packages installed, because you need to run them in the same memory space, for example. You cannot combine containers like in this graph, where you have two containers. Say, okay, I want to have both these pieces of software installed. So it's a bit of a fundamental problem now with how distributions are organized, and there are distributions that work around this, like Nixos or whatever. And but Docker doesn't support this now. So in theory, things like Nixos could solve this. But anyway, if you want to know more about it, you can talk to me. So yeah, future work is the streaming support. I need to create a solution for radio astronomy to have more efficient data transfer between the nodes, and with that, maybe we should create something like Kliko Compose. That way, it's the same as Docker Compose, where you can combine these services into a beautiful, amazing piece of art. So yeah, Kliko, check it out. It's open source. It's documented as best as I could. It's unit tested as sort of good as I could, and it supports all the Pythons. Yeah, just check it out if you want. And I'm working on my first scientific paper. I'm doing a PhD in South Africa, actually, and which is a struggle. So, but if you're completely in the kind of stuff, then talk to me. I can give you a sneak preview. Yeah, so that's it. Questions. Also about Cape Town, if you want to know more about. This is also Cape Town. You know.
Questions? Anybody? No? well, we're almost out of time. I have one question. With regards to the Docker volumes, interplanetary file system, I don't know if you know it, sounds like a great match for your use case. It's a distributed file system based on the blockchain kind of in this area, so you might want to look into that. It would be awesome to have that kind of file system for this kind of data. But interplanetary file system, IPFS.org, I believe. Have to check it out. Check it out. Any other questions?
Is it like Flocker FS or something?
No, well, check it out. In that case, I'd like to thank you for an awesome presentation. I think an awesome tool as well. I hope you all the best with your tool, and let's support him. Give him a big hand. Thank you.